Okay, previously we talked about steady-state error for unit feedback systems, and we found out equation 11. We mentioned that what this means is that the error depends on the input and the transfer function of your system. Notice that this is not the equation for every feedback system. This is only when you have this specific design, a unit feedback, and then you have G times GC. If the system, which is the feedback system with unit feedback, satisfies conditions for final value theorem, specified conditions for final value theorem, then we can use final value theorem, right? So here we can use final value theorem, which means that I should multiply this by an s and then take the limit when s goes to infinity to 0, and that would be equal to steady-state error. All right, so let's think about it. This is gonna be the steady-state error, and I want to find out what the steady-state error of a system is. Now, what we are gonna see in the next few slides is mentioning what happens for different values of R, and then the conditions that we need for G times GC to make steady-state error 0. Remember, we want the steady-state error to be 0. We mentioned that for open loop systems that is not possible. It seems that we always are going to have some steady-state error, but for closed loop systems we seem to have some ways to make steady-state error 0. All right, previously, if you remember, we assumed that for open loop systems we found out the steady-state error for the input, which is a step with magnitude capital A. Let's do the same thing here. Let's substitute R of S with capital A divided by S. If we do that, the S simplifies with S, so we are going to have the limit, which with capital A in the numerator, and then in the denominator we are going to have 1 divided by 1 plus GC times G. Now the numerator is just going to be a number, and 1 is just a number, so this limit can come inside and just affects the denominator's term, which is GC times G. Right, so let's see what that means. So the steady-state error of a system with unit feedback, when the input is a step with magnitude of capital A, can be found from equation 12. And I want this to be 0. I want the steady-state error to be 0. I want my system to be able to perfectly follow the inputs. Okay, how is that possible? How can equation 12 to be 0? Well, it's a fraction. Numerator is a number. It can't be 0. The only way I can make this 0 is if the denominator is infinity. So this is 1 plus this limit should be infinity. I want error to be 0, therefore this fraction should be 0, therefore the denominator of the fraction should be infinity, which means that this limit should be infinity. When would the limit of something be infinity? When the variable of that thing goes to 0. When would the limit of a function, when the function is being evaluated at 0, go to infinity? What do I need? I need this function to have s in its denominator. So if I want this to go to infinity, what should be the condition on GC times G? Well, it needs to have s in the denominator. It needs to have s equals to 0 poles. Okay, now let's see two definitions here. Now that we talk about having s equals to 0 in the denominator and evaluating system at s equal to 0, let's see these two definitions. The first one is the DC gain. The DC gain is the value of your transfer function when it's being evaluated at s equals to 0. Notice that DC gain only is defined for stable systems, so systems that have poles on the right-hand side, they have positive poles, they don't have DC gain. The second definition is system type. The number of integrations or the number of S's in the denominator is the system type. So here, if I write my GC times G as equation 13, so a bunch of zeros, a bunch of poles at P1, P2, P3, P5, P10 until PQ, and a bunch of poles at the origin, this system's type is capital N because it has N poles at the origin. Okay, so now equation 13 is showing me a general possibility for the transfer function. So going back to steady state error, if I want my system to have a steady state error of 0, we want to see what is the required condition. What happens if the system type is 0, meaning that if GC times G has no poles at the origin? Well, if that's the case, when I put S equals to 0 here, I'm just going to have a bunch of Z's in the numerator being multiplied with each other, and then a bunch of PK's in the denominator. So I'm going to have a number here added with 1, and then another number in the numerator. So it's never going to be 0. So if I have type 0 systems, I am going to have a steady state error. This is not good. So for whatever I explained here, a feedback system with unit step as input, and when my feedback is unit feedback, seems that type 0, if that system is type 0, I am going to have steady state error. If I have a type 1 system, that means that I have one S in the denominator. So if I take the limit, GC times G is going to be infinity, and therefore ESS is going to be 0. Steady state error is going to be 0. And if I have higher type systems, I'm just adding more and more S's to the denominator, which means that the limit would be again infinity, and I'm still going to have steady state error equal to 0. So if I keep doing this, so this was the first column, when you have a step with magnitude capital A. If you, rather than having a step, having a ramp or a quadratic, you can do the same thing again for system type 0, 1, and 2. And you're going to see that we are going to have this table. Now, I encourage you to try to do that, try to do the math. Again, don't memorize this table. If you see a problem like this, you have to actually do the math and find out based on the system that is being given to you. You should do the math and find out the steady state error. Okay, example, what's the steady state error of the system? Unit feedback system, if the input is a ramp, which means it's T. Well, the error is defined as this. I want to take the limit. I want to substitute 1 over s squared for r because we have a ramp. Take the Laplace transform of t, it's going to give me 1 over s squared. And then I'm going to have another s here, additional s, because I'm using final value theorem. So then if I simplify it, take the limit, it's going to be 0, which is the result we would get if you would go to this table. But again, that only is happening because of the certain shape that the example has. Okay, consider the previous problem, but feedback gain is the constant value of 2. So rather than having a unique feedback, now we have a feedback with value of 2. What's the steady state error to the same input? Well, we should find the transfer function, the closed loop system's transfer function. We do that, we are going to have this transfer function. So we are going to have poles at negative 1.6 and 0.3 plus minus 1.02. So we can't use final value theorem. So table 2 is not going to be useful anymore. And this system's output to a ramp input is going to go to infinity because we have 2 poles on the right hand side, which means we have an unstable system. All right, another example. For the following systems, find the type, order, poles of the system, and zeros of the system. Think about it. For this system, what's the type? Type was the number of poles at the origin, or s equals to 0. 2, right? So the type of the system is 2. What's the order of the system? Order is the number of poles we have. 1, 2, 3, 4, 5. So the order is 5. What are the poles and what are the zeros? Well, I have 1 0 at negative 3, and I have 5 poles at s equals to 0 twice, s equals to plus 5, and then s equals to negative 1 twice. How about this system? What's the type of this system? Well, there is one s here, so the type is 1. What's the order of this system? Which means the number of poles we have. Well, there is 1, 2, 3, 4, 5. So the order is 5. What are the zeros and poles? I have a 0 at the origin at s equals to 0, and I have a 0 at plus 1. My poles are going to be at the origin, plus minus 2, and then plus minus j2, or 2 times j. Okay, another example. Consider the system below. Find the system steady state error to a step with magnitude capital A. I encourage you to pause the video, try to do it, and then look at the rest of the video, or look at the rest of the slides.